Okay, so now we're starting section 6.3, where we'll be looking at how to do confidence intervals for population proportions. In this section, we'll be figuring out how to find a point estimate for the population proportion, construct the confidence intervals, and also determine the minimum sample size. First off, we need to look at the population proportion. That's the probability of a success in a single trial of a binomial experiment. So our population proportions will be looking at things that meet the binomial criteria, which means there'll be only two possible outcomes, yes or no, success or failure. We're going to denote the population proportion by the letter P, and the point estimate is the proportion of successes in the sample, and it's going to be denoted by P hat, which is equal to the number of successes in the sample divided by the number in the sample, the actual number in the sample. And we call this symbol here P hat. So in order to find a point estimate, the first thing we need to do is find P hat, and then we can estimate Q hat, which is equal to 1 minus P hat. For example, in your survey, if 65% said yes, then 1 minus 65% or 35% said no. And you always, in their formulas, we denote P hat and Q hat by their decimal equivalent, 0.65 and 0.35, but usually in your final answers you denote them as percents, like 35% and 65%. All right, and we denote Q hat with red Q hat. So let's look at an example. Suppose in a survey of 1,000 U.S. adults, 662 said that it's acceptable to check their emails while at work. Let's find the point estimate for the population proportion of all U.S. adults who say it's acceptable to check their personal emails while at work. Well, our sample size is 1,000, and we had 662 yeses, in other words, successes. So P hat is equal to the number of successes in the sample divided by the total sample size, which is 662 divided by 1,000, which is approximately 0.662, which is equivalent to, as percent, move the decimal to the right 2 spots, or 66.2%. Confidence interval for estimating the population proportion P is similar to all the confidence intervals we looked at before. A confidence interval is always equal to the point estimate plus or minus the margin of error. The big difference here is our formula for our margin of error. The margin of error, E, is equal to the critical value, which, remember, are numbers like 1.96 for 95%, 1.645 for 90%, and so forth, times the square root of P hat times Q hat divided by N. All right, so in order to construct a confidence interval for P, the first thing you need to do is figure out what is the sample size and the number of successes in your sample. From there, you can calculate the point estimate, which is equal to the number of successes in the sample divided by the sample size. Then we need to verify that the normal distribution can be used to approximate this confidence interval. To do that, we need both of these two conditions to be true. We need N times P hat to be greater than or equal to 5, and we also need N times Q hat to be greater than or equal to 5. Then we find our critical values. Remember, most of you have already learned that the Z critical value for 95% confidence interval is 1.96. For a 90% confidence interval, it's 1.645. For a 99% confidence interval, it's 2.575. Any others, you have to use your standard normal table to look them up. Then find the margin of error using this formula. Then take that margin of error and add and subtract it from your point estimate P hat, and this will give you the confidence interval. So let's look at an example on finding a confidence interval. We're going to continue on with our example we saw a minute ago with the U.S. adults who think it's acceptable to check personal emails while at work. Remember, we surveyed 1,000 adults, and of that 1,000, 662 said it is acceptable to check their personal emails while at work. Let's construct a 95% confidence interval for the proportion of all U.S. adults who say that it's acceptable to check their personal emails while at work. Recall from a few slides ago that p hat was approximately 0.662, which means q hat is 1 minus 0.662, or 0.338. Now let's check the conditions. Is n, which was 1,000, times p hat, which was 0.662, which is equal to 662, which is certainly greater than 5, and n times q hat, which is 338, is also greater than 5, so our condition holds. Then we can compute the margin of error using the formula. Remember, for a 95% confidence interval, the critical value is 1.96 times the square root of p hat in decimal form, q hat in decimal form, divided by the sample size, which is approximately 0.029. We then use the margin of error and add and subtract it from the point estimate. To get the left endpoint, we subtract the margin of error and get 0.633. For the right endpoint, or the upper endpoint, we add the margin of error to the p hat. And so we know that the population proportion of all U.S. adults who think it's acceptable to check their personal emails while at work is somewhere between 0.633 and 0.691. So we are 95% confident that the population proportion of all U.S. adults who say that it's acceptable to check personal emails while at work is somewhere between 63.3% and 69.1%. Now, sometimes we need to find the sample size, the minimum sample size for a given margin of error. We saw this when we were in 6.1, but this formula is different. So n needs to be at least really greater than or equal to p hat times q hat times the critical value divided by E quantity squared. Okay, now this formula assumes that you know you have some kind of estimate for p hat and q hat. If you don't, then use p hat equal to 0.5 and q hat equal to 0.5. All right, so here's an example. Let's find the minimum sample size when no preliminary estimate is given. Now we wish to find this minimum sample size for a 95% confidence interval for the proportion of registered voters who will vote for your candidate, and we want the estimate to be accurate within 3% of the true. The number that comes after within, or the words like no more than, that is your margin of error. So in this case, since we do not have a preliminary estimate for p hat, we're going to use p hat equal to 0.5 and q hat equal to 0.5. Remember, our confidence interval was 95%, and the critical value for 95% is 1.96. The margin of error was 3%, written as a decimal is 0.03. So we put that into the formula, 0.5 times 0.5 times 1.96 over 0.03, and this quantity is being squared. And we get approximately 1067.11. But we need 1/1100th of another person, which means we need a whole nother person. So with minimum sample size, just like you learned in 6.1, we will always round up to the nearest whole number. So we need to have at least 1,068 voters. Now suppose we are given a preliminary estimate for p hat that is 0.31. So let's again find the minimum sample size for the same problem. If p hat is 0.31, then q hat is 1 minus 0.31, or 0.69. Again, the confidence interval is 95%, which means my z critical value is 1.96. My margin of error is still 3%. When written as a decimal is 0.03. The formula now is p hat 0.31 times q hat 0.69 times the critical value 1.96 divided by the margin of error in decimal form. This quantity right here is squared, and we get 913.02. But since we have any portion of a decimal at all, no matter how small, we always round up. So we need at least 914 voters. All right, so that's the end of section 6.3. You can now go to Course Compass and try the homework for section 6, homework 6.3.